Okay, everyone, let's get started. Were there any issues with the lab 1? I got the sense everyone felt that was pretty easy, right? Wrong? Depends on how well you remember 212, I guess. Or 212, yeah, 212. Okay, so the next lab we're going to assign today, and it's another kind of intro lab. See, I've got the lab sheet here on Blackboard. So this will be the first lab where we use the FPGAs, and the objective is to not design a CPU, but instead to just put 7-segment decoders on there that will interpret each group of 4 switches as a hexadecimal value, right? 4-bit hex value, right, from 0 to F, right? And then we'll feed those into a 7-segment decoder, which will output 7 bits that will go out to each of the 8 7-segment displays on the board, right? Does that make sense? So I don't know if you guys, I think you guys did a 7-segment decoder in 211. Okay, so the board has 18 switches on it. So in order for us to have full access to the 8 7-segment displays, we'd have to have 32, right? 8 times 4, right? But we don't have 32, we only have 18. So we can't actually use those 18 switches to set all 8 hex displays. We can only access 4.5 of them, right? Make sense? 4.5. So the idea, basically we're going to have the ability to put any value on the 7-segment displays from 0 to, let's see here, where's the value? 0 to 3FFFF. Let's see. Make sense? So there's 18 switches, and if you divide that by 4, right, you get 4.5, and that half will give us the ability to set a value from, we just get half the bits. We just get 2 bits instead of 4. So we can put a value from 0 to 3 on there, right, instead of 0 to F. Make sense? So we'll go over the details of this in lab. The lab sheet's on here, but just to quickly go through it, it says your objective is to develop a 7-segment decoder module, and I'll talk about what that is in a minute as I introduce SystemVerilog. And it will convert a 4-bit binary value into a 7-bit control code for a 7-segment display. And then we'll instance it 8 times. And then we're going to connect the switches into, not all 8 of them, but into 5 of them, right? And then the other 3 will have to be, unfortunately, just hard-coded to 0 for now, their inputs, right? And then we have some instructions on here how to compile your code and deploy it to the DE2 board, but I'll talk more about this here in this lecture. Okay, so this is another intro lab. Usually everyone finds this one to be pretty simple. This one's just to introduce you to the tools and the FPGA boards and the simulation tool that we use, ModelSim, which I'm going to introduce today. Okay, so that's the lab. I also have a quiz. The first quiz is on, I need to reveal it. So I normally assign these quizzes on Monday, and then they're due on Friday. You have an unlimited amount of time to take it, and you can have 2 attempts at it. And this quiz just has 10 questions. So this just gives you practice for the material that we covered in class, and allows me to track how well I'm getting the material across, and if I'm going too fast or too slow. Okay? All right, so don't forget to take the quiz by Friday at 11:59 p.m., so basically anytime this week. All right, so now we're going to move into the hardware portion, logic circuits and SystemVerilog. So I talked a little bit about this already. So hardware designs, digital circuit designs can be defined as behavior, which is Boolean logic. You have a question?
Yeah, question about lab 2. This is the one where we start doing stuff as like partners, right?
Sorry?
Lab 2 is the lab where we start doing stuff as partners, right?
Yes. Yeah, that's a good question. Yeah. Technically, all the labs you can work with partners. Lab 1 was not ideal to work with a partner since it's running code. So I think a lot of you guys didn't, some of you guys didn't have partners, other ones did. It doesn't matter to me. Lab 1 is kind of optional groups. But yeah, Lab 2, you're going to want to form a team. If you don't have a team now, you should form a team for Lab 2. Yep, thank you. Okay, so behavioral is Boolean logic. You guys learned that in 211. Structural is when you define your design as a schematic, or sometimes it's called a netlist. It's basically a modules or components that are in a design and they're connected with wires. And then there's a physical representation where the modules or the components in the structural design have to then be actually mapped to some kind of physical hardware. So on an FPGA, this would be things like LUTs and the components that are in the FPGA fabric, LUTs and RAMs and multipliers and that kind of stuff. And then you have to use resources to connect them, some kind of wiring resources or routing fabric, routing tracks, wire tracks to connect them. So in 211, you guys did that with the breadboards. You took your schematic and you decided how you would assign each of the components in the schematic into one of the slots on those 7400 level chips. Yes?
I don't think we did breadboards in 211.
You didn't? Did any of you do breadboards? Oh, use Logisim. Oh, that's right. Yeah, they moved to Logisim. Okay, well, that's what you should have done in 211. If we didn't have a degenerate form of 211. No, I shouldn't say that. That's harsh. No, Logisim is good too. But the breadboard is, these days it's seen as kind of elementary. But the point I'm trying to make is that it illustrates the concepts that everyone from Apple to Intel uses when they design a new chip, which is you have to, you have these 3 different representations of a design, and the physical one is where you actually allocate these kind of logical components. They have to be allocated onto physical entities in the physical design, right? So you do this with an FPGA. You can do this with an ASIC if you're doing ASIC design, where you're taking these gates and actually putting them on an ASIC substrate, like a chip substrate, right? And in the case of breadboard design, you're doing it by deciding which one of these gates you want to assign to the little slots in those 7400 chips. Those 7400 chips usually have, like, for example, 4 AND gates. So each one of those chips has 4 gates on it, and you have to decide which of those 4 you want to use for each of the gates in your structure, in your schematic. Does that make sense? Same thing with a circuit board design too. In a circuit board, when you lay out a circuit board, you have a schematic, and then you go and have to place the footprints for each of the modules on the schematic onto the physical board layout, right? Okay. So yeah, I think I showed this last time. So in this class, we're going to use Verilog as the behavioral to define the behavior. We'll also use it to define structure. In this case, I'm showing this is actually a generated graphical structure from a Verilog description. So in the tool, we use this tool called Questasim, and you read in your Verilog. That Verilog can either be behavioral code or structural code, meaning that it can have logic expressions in it, or it can have components with wires connecting them in it. And then you can go into the RTL viewer in Quartus, and it'll actually generate a picture, a schematic for you. So this is machine generated here. This is not, no one actually drew that. And then, like I said, these guys are mapped onto the FPGA when you go to deploy it on the FPGA, right? So you have this design is purely virtual, conceptual, but then when you put it on the FPGA, it becomes real, it becomes tangible, right? You deploy it in the hardware, it becomes a real circuit, right? Okay, so yeah, so I already talked about that. Okay, so hardware description language was designed to manage the complexity of large-scale designs. So people, when I first started learning about this stuff, they would say, you know, a typical processor has hundreds of millions of gates on it, right? Or billions of transistors. I think nowadays they have tens or hundreds of billions of transistors. And I used to laugh at that and say, come on, that's got to be hyperbole, because who's designing a system with 100 billion parts on it? That's impossible. It's just, there's no way. But it turns out the way that it's done is using CAD tools that manage the complexity through these three concepts: abstraction, hierarchy, and regularity. So when you do a design, hardware design, when you look at any design file, there's usually a relatively small number of components in there, right? And the reason for that is because it's hierarchical. Each one of those components is actually hiding complexity inside of itself, right? So we call that, you know, if you take a component in a block diagram and you want to look inside of it, you want to go down one level, I always call that drilling down. So you're taking a component and you drill down. So it's kind of like a, you know, nesting doll. You have a component in there and you open that up and it has other components, and you can pick one of those and open that up and there's other components. So that way any version of the design you look at looks relatively simple because it's hiding the complexity through the hierarchy of the design. You have kind of a root, you know, of the tree, sort of like their top level design, and that top level design has a few components, but then you can go inside those components and there's more components, and you can go in those components and there's more components. Likewise, there's this concept called regularity, which is where you basically design a relatively few number of these unique components, but then they're kind of reused a bunch of times, which ends up multiplying the number of like transistors in each one of those components gets multiplied by however many times you stamp it out. So for example, in a GPU, they'll say, well, you know, a GPU has like 1,500 cores in it. It's like, well, who could design that? Well, because they only design one core and then they stamp out 1,500 of them. So thus it's very easy to design a GPU because they only have to spend time designing 1/1500th of the die, and then the rest of it is copied and pasted, right? That's why, you know, GPUs tend to be very scalable in that way. CPUs are a lot less regular. They have a lot less repeating structures on a CPU, and therefore new CPUs are much harder to design than new GPUs because they have a less regular structure in them. You can see that from the die pictures. I showed you, I think in the last lecture, die pictures of a CPU, and they don't look, there isn't like quite as strong of a repeating pattern inside of a CPU design as there is in a GPU. And so that's regularity. The idea here is that you want to minimize the number of unique modules you have to design so you can maximize your ability to reuse them. And then, you know, abstraction is just saying that, you know, that you're hiding details in the design, you know, by essentially by using hierarchy, right? So for example of that, like if you have a CPU, a CPU might be the root level design, the top level design, and then there's like 4 processors. Those processors are just copied and pasted. And then inside one of the processors, if you drill down, you'll see that it's comprised of functional units and a register file. And then you can, multiple functional units, you drill down in a functional unit and you'll see, well, there's a floating point unit. And then you drill down there and you find out, well, the floating point unit is just a comparator and an adder and a shifter. And then you drill down in the comparator and you say, well, that actually has a subtractor in it. And then you drill down in the subtractor and you see, well, that has an adder in it. And then you drill down in the adder and you see that's just a bunch of full adders that are in an array, right? So that's how hierarchy works. And so HDL is designed to leverage these concepts. by taking the design and composing it into these modules. Modules are designed to be reused and abstracted. And a module is really another name for a logic circuit. And a logic circuit is, you could think of it almost like the hardware version of a class in software, where you have like an interface. There are top-level interface to each module, inputs and outputs. And then there is a functional specification that's defined within it. So it's internal behavior. And those first three are what you typically see in an HDL, a hardware description language. There's also a fourth, which is the timing specification. That's usually not something you actually deal with in the HDL level, because the timing specification is inherently linked to the underlying technology that you deploy the HDL into. And so you typically have to deal with that with the CAD tools. But we'll talk more about that later. So for example, here's a simple logic circuit where you have A, B, and C are inputs, Y and Z are outputs. And then there's the functional description is this structure, and the structure has these three modules that are instanced and wired, and some of those wires internally are connected to the top level I/O pins. These are called ports. So you can see that this module is connected to A and C on the input, and then it's also in this case connected to Z. But notice there's also some internal signals in here that are not exposed to the outside world, right? Namely this N1, this signal, right? That's just an internal, declared internally. So you could think of that like if this were a class, that would be kind of like having a private variable, right? A private member inside the class. Make sense? Okay, so there's two types of logic circuits. And by the way, when I say logic circuits as opposed to like any other type of circuit, like an analog circuit, right? Logic circuits are digital circuits. There's two types. There's combinational logic, where the outputs are a function of only the inputs. So you change any of the inputs, and the output may be updated to reflect that change. And then there's sequential logic that involves memory. So in a sequential logic circuit, the outputs are a function not only of the inputs, but of the history of inputs that were given to the circuit, because it has a memory, right? There's memory. The memory can be RAM, or it can be flip-flops or latches. And hopefully you learned a little bit about that in 211. Okay. So in combinational logic, you have to make sure that every element inside your combinational logic circuit is combinational. So in this lab, in lab 2, these 7-segment decoders are purely combinational. There's no memory. So we're going to connect the inputs of these modules directly to the switches on the FPGA board, and then the outputs will go straight to the hex decoders, which are also connected directly to the FPGA. So we're going to connect these things between the input pins and the output pins in the FPGA, which will bridge together the switches and the hex displays, right? That's the goal. And there's no memory involved there. Okay, and then the other thing is, in this class, I'm going to be showing you a lot of schematics on the slides. In fact, when we design the CPU, your goal really is to just convert schematics into HDL code. That's kind of what lab 3 and 4 is, right, in a nutshell, right? So you have to get used to reading. There's two things that I'm hoping to get across this semester. The first is that you should be comfortable reading schematics. And the second is that you should be comfortable reading timing diagrams. So for schematics, and you've seen some of these before, I'm sure in circuits class in 211 and 212. Schematics are when you have some, usually it's like a block diagram. You have a bunch of blocks, and then there's wires that are connecting them. Typically, the left side of the diagram is where your inputs are coming from, and the right-hand side of the diagram is where your outputs are going to. So usually, not always, but usually you kind of read them from left to right. Data generally flows from left to right by convention, right? And then when you design a schematic and you want it to be readable, you try to avoid bends in the wires as much as possible. But that's kind of more of an art than a science to actually be able to draw a schematic and avoid bends and make it readable. Because as this complexity goes up, it starts to turn into a rat's nest. You end up with blocks and wires, and it becomes difficult to keep track of where all the wires are coming from and going to. In this class, I try to do my best to manage that complexity, but sometimes it's still a little difficult to follow. The other thing is, if you have two wires that have to cross each other, which happens, the problem is that when you have crossing wires like this, it is more often the case that they're not supposed to be shorted than they're shorted, right? If they're shorted, in other words, if these wires are supposed to be connected, you generally will see a dot there. But if there's no dot, you can assume that they're not connected, right? They just cross each other, but they're not connected. However, if there's a T-junction like this, that definitely means they're connected even without the dot, right? Because why else would you have that T if they weren't intended to be connected? So the T-junction is basically what's called a fan-out, where you have a wire coming here from the left, and it splits off into two directions, splits off to go to two different inputs of two different modules. But when it splits off, instead of splitting like a fork, generally one of the paths will go horizontally and the other one's going to go vertically, right? So now it may be the case that the input is coming from the bottom and it splits, to the left and right. That's possible too, right? But the point is if you have a T-junction, that there's a short there, they're connected. All right, so I'm going to jump around a little bit and talk about there's data types. So in Verilog, and there's an equivalent to this in VHDL. So there's two languages that are most commonly used for designing large-scale digital logic circuits. There's Verilog and HDL. We're learning Verilog, but all of the things you learn about Verilog, it maps to VHDL. Both languages have a data type in which you have multi-state logic. So basically, in a digital logic design, you would expect every value to be binary, right? Because that's the whole point, right? Is that you're designing a digital logic circuit, and digital means binary, 0 or 1, or true or false, or high or low, or asserted or not asserted, right? But there are additional values when you simulate an HDL design that these values can take on. For example, in VHDL, you can have a signal that's coming from a memory element that has not been initialized. Like, in other words, it hasn't been reset or it hasn't been set yet at this point in time when you're looking at it, right? Now, in an actual circuit, if you have a memory element and you don't initialize it, it's going to be random. It actually comes up as a random value. Like when you power up a chip and it's got a bunch of flip-flops on it, those flip-flops are going to be randomized. On an FPGA, you get to cheat a little bit because in FPGA, when you configure it, you're actually initializing everything on the FPGA during the configuration process. So on an FPGA, not when you power it up, but after you program it, you know that all of the memory elements on there are going to come up as zeros. But on an ASIC, like on a regular chip, memory comes up randomized, right? But when you simulate HDL, if you don't initialize memory, in the simulator, it needs to come up as uninitialized because you can't assume that, when you design the HDL, you're designing a generic digital logic circuit, so memory is uninitialized. So there's a special value for that. In Verilog, it's X. In VHDL, it's U, right? But it's not 1 or 0. Likewise, there's also a special one for whenever you have 2 logic gates or more whose output is connected to the same wire, shorted together, right? If you have 2 logic gates that are both driving, in other words, they're trying to set a value on the same wire, they can potentially be in conflict if one of them is trying to put a 0 on that wire and the other one's trying to put a 1 on the wire, right? So in general, if you have a logic circuit, you should only have one logic circuit's output connected to each wire in your design. Now there's some exceptions for that. There's things called tri-state buffers where you can electronically disengage a module from a wire, its output, right? So there's cases for that. But in general, if you don't have a tri-state buffer, you just have two logic circuits. If they're both trying to fight over the value of a wire, they're said to be in conflict. And in fact, this is the most common error we have in this class. The most common bug that you will encounter is double driving a signal or putting a signal in conflict. And so there's a special value for that, which in Verilog is X. There's also a value for a don't care. I don't know if you remember from 211, but sometimes you don't care. You have to have a circuit that sets a value, but you don't care what the value is. And so you can leverage that when you're minimizing the logic, right? When you're trying to reduce the complexity of the circuit. So there's also a value for a don't care, which in Verilog is also X. And then finally, there's a value for high impedance or undriven. And this is for the tri-state buffer I was just mentioning. If you have a tri-state buffer, or if you just forget to, like you have a signal that there's nothing driving it. There's no circuit it's not connected. You know, you have a wire, but you don't have any outputs connected to that wire. Then it will be floating, or Z. It'll have a value of Z. So to summarize this, Verilog has what's called four-state logic. It has a 0 or 1, and then it has X or Z. The problem is that X means three different things. It can mean don't care, don't know, or conflict, which is something I don't like about Verilog. In VHDL, they fixed this problem. In VHDL, a don't care is a dash, a hyphen. Uninitialized is U, and X is conflict, right? So VHDL, I think, has fixed state logic, but this is one of the limitations of Verilog that you should be aware of. So the idea is that if you simulate your design and you see any X's in there, unless you set them to X as a don't care, unless your logic actually was explicitly setting to X because it's a don't care, it probably means you got a problem, a bug. Okay? Everyone with me? So there's this type called logic, and it's an enumerated type containing the values 1, 0, X, and Z. 4 values. Yes? Yeah, the undriven value is either if you have a wire that you declare. Like I say, I declare, so you can instance a wire by declaring it. You just, like you would do a variable in a programming language. You say logic space X, right? And so I declare a value X, but I don't actually use X. I don't connect it to anything, or I don't connect it to any outputs. I might connect it to some inputs, but if I don't connect it to any outputs, there's no circuit to set that value of X, so it'll come up as Z. Alternatively, you can set it to Z in your code, and if you do that, it will imply that there's a tri-state buffer, which means you can disconnect the wire. Now on FPGAs, it's very rare to use tri-state buffers. I don't think I've ever used one. But it's possible. So in other words, it can be a consequence of your design, or you can explicitly set it to Z. Okay, so, sorry, I already mentioned this. So contention or conflict. So here's an example of this where you've got two inverters here, and their outputs are shorted together. Okay, and in this case, one of them is driving a 0 or trying to basically what's called pull the wire down to ground. There's a transistor trying to pull it down to ground. The other one's trying to pull it up to 1, meaning that there's a transistor on the other inverter trying to, short at the power supply, VDD. And this ends up creating a low impedance path between power and ground, which means it's a short circuit. So, I mean, if this happens on an FPGA, if it allows it to happen, if the tools allow this to happen, then you could damage the device. Okay, Yeah, and this is the Z, so I got ahead of myself a little bit. So you have this notion of Z, which stands for high impedance or floating or undriven. This is if you have a tri-state buffer. So this is what a tri-state buffer looks like as a schematic symbol. There's an input and output that are basically just shorted whenever the control input here is E is asserted. And if E is not asserted, then you get a high impedance value for Y. Okay, so I'm going to circle back around to hardware description language. Hardware description language, usually called HDL. Sometimes it's called RTL, which stands for Register Transfer Language. There used to be a difference between those two, but now they're the same. Everyone just uses those terms interchangeably. There's really only two. I mean, there's more than two. In fact, there's thousands that have been developed over the years, but no one ever uses those ones. They only use these two. So unlike regular programming languages, for whatever reason, these two, which were both developed in the early 80s, for some reason they sort of just keep persisting. So there's VHDL and Verilog. The history is kind of fascinating. So VHDL is an acronym that stands for VISIC HDL, or VISIC Hardware Description Language. And VISIC is another acronym that stands for Very High Speed Integrated Circuit. So the quick history is that the Department of Defense used to have to order a lot of chips from vendors, from contractors, military contractors, to control things. And the problem was that when they would go out and describe what the chip should do, it had to be described in English prose, right? Just in plain English. Like, the chip should take an input, and the input should control the rotation rate of the tank turret, and the input should be a 7-bit signal and should be in radians per second. They would just have to describe it, which was a very imprecise way of defining the behavior, the specs. So they launched this effort to develop this standardized language in 1981, and it was originally just designed to just describe what a chip should do, but eventually it became an IEEE standard, and also people started designing auxiliary software for it, like a simulator, where you take the VHDL code and you could actually simulate it, and then after that, they came out with these tools for synthesis, where you could take the code and automatically generate gates and wires from that code, like that you could use it to compile the code into hardware, right? But that was never the original intent. I don't believe so anyway. I think the original intent was just to use it as a way to concisely describe the behavior of hardware. And then Verilog came out of the private sector. So it was developed 3 years later by this company called Gateway Design Automation. I think they were a small company, but they were later bought by Synopsys, I think. They were eaten up by a bigger company. Verilog was, I think what happened is that VHDL is based on Pascal. So VHDL is designed to be a very verbose language because they wanted to be very self-documenting. So like if you define a function, you have to actually type out function. If you define an array, you have to type out array. And so it's a lot of typing. But you don't have to put any comments in there because the language is by its nature is self-documenting. And it's like case insensitive like Pascal was. But some people looked at that and, it's the same thing now, like with, people that are Python snobs that make fun of MATLAB coders. They looked at that and they said, that's a crap, language. Like programming languages should be case sensitive. And also there's too much typing involved. Self-documenting is dumb. The program should be minimal number of characters typed to get the job done. We don't want to type a lot. We don't want to type out function. You just put a left parenthesis and then obviously that's a function, right? That's kind of the idea. And so if you want to put comments, you can put comments, but the language shouldn't be self-documenting, right? So the snobs came out and they created Verilog, which does exactly the same thing as VHDL. It's just a different syntax. But all the semantics of the language are identical. completely identical, just different syntax. So we used to teach this class in VHDL, but I didn't like all the typing either. I got sick of all the typing. Type everything out. Everything had to be typed out. You had to type 10 times more characters to write an equivalent VHDL as compared to a Verilog. So, and also I realized that in industry, most companies are using Verilog. However, in academia, it's still sort of more VHDL, right? But the good news is, if you've seen the textbook that we have in this class, every time they show an example of the code, they show them side by side in the textbook. So, if you learn one, you can learn the other very easily. It's not like saying, if you know C, you can't learn Haskell. They're just totally different semantics, right? But if you know VHDL, you can learn Python and vice versa. I'm sorry, Verilog rather. If you know VHDL, you can learn Verilog and vice versa. Okay, so Verilog became a standard in 1995, so much later. Verilog was an IEEE standard in 87. Anyway, now they call it SystemVerilog because they've extended it into a bigger language. Okay, so I mentioned this already. So there's two things you can do with this code. You can simulate it, or you can synthesize it. In this class, we use two totally different tools for this. We use a tool from a big company called Mentor Graphics, which was actually recently bought by Siemens. I guess, I don't know if they even still say Mentor Graphics on it anymore. But anyway, the simulator is called ModelSim, and we use it because it's an industrial strength. Oh, sorry, they renamed that too. It's called Questasim now. Sorry. Questasim, which used to be called ModelSim, which is now owned by Siemens, previously owned by Mentor, and previously before that owned by a company called Rhinosoft. So one of the issues with CAD tools is that they tend to be bought by progressively larger companies, right? But the point is, though, is that this tool is industrial strength. So if you go to work for Apple or Intel, you'll either be using that one or you'll be using the one from Synopsys called VCS. They're both industrial strength. In this class, we are not exercising even a fraction of the capabilities of this tool. It's designed to simulate massive systems, circuits. But we wanted to teach it just so when you go in industry, you'll have experienced it. If you don't want to use this commercial tool, there are free ones available. The most commonly used one's called Verilator, which is pretty cool, actually. There's one called Icarus Verilog and Verilator. Both of them basically convert your code into an executable that you can run, just in Linux natively, which is kind of neat. And also you can more easily interact with it through C code, your software. But anyway, we're not doing that. Eventually, I'll probably switch to that. But for now, we're using this ModelSim. Okay, so all right. So let's look at some examples. So here's an example of a Verilog module. So everything is based around the concept of modules, like I said, because this is designed to exploit hierarchy and regularity as much as possible. And the concept of the module is designed to take advantage of that to manage the complexity of design. When you synthesize, modules disappear because the hierarchy of your design gets flattened into one monolithic sea of gates and wires. That's completely unreadable, right? But the modules are there for the human factor, just for readability. But in reality, they don't really translate into something physical in the real world. They're just virtual because, like I said, the modules end up getting flattened into just one big sea of wires. So you have this thing called module example. Again, the name example is just for human consumption. This is irrelevant when you convert it to hardware. And it has 3 inputs, A, B, and C, and an output called Y. Now, this is one thing that's a little strange here. Notice it says input logic A, B, C. The reason that works is because B and C, because they were not given a type, they inherited the input logic type. Does that make sense? So basically, if you have multiple inputs, that's a shortcut you can use. You don't have to do it. You could say input logic A, comma, input logic B, comma, input logic C. As a matter of fact, if you are serious about your code being beautiful and readable, right, you wouldn't even put those on one line. You would do what my former student Charles would do, and you would put every input and every output on a separate line with line breaks, and you'd have them lined up in a column, real nice, indented, right? But this is a quick and dirty thing where I just say input logic A, B, C. And then notice that this is the weirdest thing about Verilog. Well, maybe not, but notice there's a semicolon here. After the module, there's a module line, and then there's a semicolon after it. Why? Why is there a semicolon there? I mean, that module line opens the module, it starts the module. There should not be a semicolon there, but they put a semicolon there. And then they end it with end module, as opposed to like, braces or something. No semicolon after end module. So there's a semicolon on the module line, no semicolon on the end module. Unclear why. And then, of course, in between those is where you have the functional description of the module. And in this case, there's only one line of code, and this is called a continuous assignment statement or a concurrent assignment statement. So when you write code in any other high-level language, those languages are going to have something called sequential semantics, which means that when you run code, the computer is like on one line of code at a time. Right? There's something called a program counter inside the hardware, and it tracks where it is in the program, right? But in Verilog and VHDL, they use concurrent semantics, which means that usually, and there's some exceptions to this, which I'll cover, but in general, if you have these assign statements, the order that these are in makes no difference in the code, right? There's no notion of like where you are in the code. Because in this assign statement, the way it works is any signal that's referenced on the right-hand side of the equal sign is considered an input. And when the state of any of those changes at any time, it activates the assign statement and it will update the output immediately. So what that means is that in order to run this code, you have to either put it in hardware, in which case that line of code is a circuit that's just running continuously. That's why they call it a continuous assignment statement. Or you can run it in a discrete event simulator. A discrete event simulator, which is essentially what reconciles the difference between a concurrent system like this and a sequential system that you're running on a computer. And the way that a discrete event simulator works is that each one of these assignment statements can be triggered by an event, and the event that triggers them is whenever the inputs change. When any of the inputs change, it triggers them, they change their output, right? Now, when they change their output, that might subsequently trigger other lines of code, right? In which case you run those. Now, the problem with this, though, and there's a huge problem with this, is that if you have a line of code that triggers another line of code, and then that second line of code then triggers the first line of code again, you end up with a deadly embrace in which the discrete event simulator will get locked in an infinite loop and freeze. And Model Sim will freeze if you have a circular dependency like that. And those bugs, that's hard to track down, because if that happens to you, there's no way to debug it other than you have to essentially do a binary search like we did when we found the square root. You have to comment out half your code and run it and see if it locks up again. If it does lock up, then you can isolate the problem to be in the half of your code you didn't comment out, right? So you can iteratively repeat that until you zero in on where the problem is. But in general, that's the only way to debug that kind of circular dependency. You guys with me? Okay, so what this does is notice that there's an ampersand and tildes and bars. So that's literally just Boolean logic. So that's just a Boolean logic statement A, B, and C are all single bits, true or false values, and Y. So that just creates a basically essentially a 3-input Boolean logic. So when you simulate this, the way it's done, the way that you view this working is through a timing diagram like this. So you'll have this this plot where the horizontal axis represents time, and each one of these signals is arranged as a row along the vertical axis, and then each signal can be designated as being 0 or 1, right? Now logic, I'll talk about this in a minute. SystemVerilog does support multi-bit logic, and if these were multi-bit signals, then they wouldn't be 0 or 1. They would be a value within, you know, the range allowable by the number of bits you have, right? Okay, so usually when you simulate these, you have a vertical cursor. And so you put this, it's shown in blue here. So you put this vertical cursor somewhere on the timeline, and then these values here will show whatever is under the cursor. So, you know, when you debug these, usually you just put your cursor somewhere and read the corresponding value. So it looks like a logic analyzer, right? Or an oscilloscope, essentially. And so all the simulation is well, not all of it. You could also have it display, you could have it display every triggering event as just a line of text or a row, right? But the waveforms are, in my experience, the more common way of simulating these things.
State of the A, B, C, and Y is at any given time. Is that what this is?
Yeah, exactly. So A, B, and C are inputs. Y is an output. Now you'll notice that A, B, and C are changing, and they're going through a counting sequence: 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0. So they're counting basically from 0 to 7, in which A is treated as the most significant bit, and C is treated as the least significant bit. Now you might say, wait a minute, who's controlling those? Those are being controlled by some kind of a test bench, something that's driving those signals to exercise the circuit. So they're being driven by a stimulus of some kind. And then the goal of this timing diagram is to look at what Y is as it corresponds to each A, B, and C value. Now, one of the things you might notice looking at this is it seems like Y is changing exactly at the same time any of the inputs change. At least any of the inputs change that would change the corresponding logic value of Y, right? That's not realistic, because in reality, there's propagation delay through a logic circuit. That's part of that timing spec that I mentioned earlier. So one of the inputs changes. It takes a little bit of time for the output to change because of the resistance and capacitance that's in the logic circuit. However, that is not modeled here. So this is when you simulate a Verilog design, you're doing purely behavioral simulation. You're not considering any of the limitations of the underlying technology. So the propagation delays aren't in there, which means that you'll find that the output changes not instantly, but after an epsilon time delay, meaning that there is a time delay here, but it's infinitely small, but non-zero. There's a non-zero time delay. On the timing diagram, you don't see it though, right? But it exists because in the simulation, if you change the values of A, B, and C, but you don't advance the time of the simulator at all, like you don't run the simulator, then you won't see a change in Y. But if you run the simulator for any amount of time, then you will see the corresponding change of Y. That's this epsilon time delay. Now, there is a way to synthesize this and then have the synthesizer back annotate delays into the SystemVerilog code, where you'd actually see the delays. But no one ever does that. That's basically useless. The reason why is because instead of doing that, it's more useful to do what's called timing closure, which is where you take your design, you tell the CAD tools how fast you expect it to be in terms of its critical path delay, which is also it's called its Fmax, its maximum clock speed. And then the synthesizer will tell you whether it's able to achieve that or not. And if it's not, then you can go into a timing tool and figure out where the critical paths are that's breaking your timing constraint, right? But there's no reason to ever go back and simulate it with the delays intact. That's It's possible. The tools support that, but it's pointless. Yes?
Don't we schedule the clock time according to the critical path delay?
Yeah.
The longest delay will
That's right. So in this class, when you simulate the behavior, you can set the clock to whatever speed you want. It doesn't matter. When we deploy this on the FPGA, though, we have this little bit of a cop-out where we're going to use a 50 megahertz clock. And we're going to tell the tools that we're using a 50 megahertz clock. So if it's not able to make your CPU meet that timing constraint, you will get an error. It'll tell you that. You'll get a timing violation. But 50 megahertz is so slow that even in this class, without any kind of optimization, we can easily make that timing constraint on these FPGAs. Although we've been thinking about introducing that timing analysis. I'd like to do that. That's something I've always wanted to do in this class, other than just say, oh, run it at 50 megahertz, because I think you could probably get these RISC-V CPUs to run at 200, 300 megahertz, but it would take some iterating on the timing, right? And then you have to understand how to use the timing tools. In this class, though, we focus just on the behavioral design, right? Just getting the behavior, not necessarily, we don't focus too much on the deployment, the physical. Okay, so then as I mentioned, the tool actually, if you take this code, now this is behavioral code, and you'll notice that if you run it to the synthesizer, it'll actually show you the corresponding structural code, in which it actually allocates gates. And the fascinating thing about this is you'll notice that there's something goofy here, because yes, there are the right amount of inputs here, and there's the right amount of outputs here, but according to the code, there should be 2 OR gates, or 1 OR gate with 3 inputs rather, right? And there should be like 3 AND gates with 3 inputs each, right? There should be 3 AND gates, 1 OR gate, right? But there's not. Why? Why is that?
Logically equivalent.
Yeah, exactly. So this is a logically equivalent to what's written there. It's not a direct mapping. So when you guys took 211, you might have minimized that, but whenever you went from logic to gates, you would have done a direct translation, right? Whereas you'll notice that the tool here is doing a logic minimization and coming up with, I don't know by what standard that's optimal. I don't know, number of gates or delay or power, whatever the objective is, it tailored this implementation of this equivalent circuit to meet that objective, right?
Yes, I was coming to the same point that isn't that like an NP-hard problem?
Yeah. So logic minimization is NP-hard, and so is the mapping process. So you have to minimize it, and then you have to map these to the actual gates on the FPGA. Then you have to place and route, which is also NP-hard. Those are all NP-hard problems. But in practice, the thing that takes the most time is the placing and routing part. This actually, usually in our experience, is pretty fast.
It's not guaranteed to be optimized output, but we believe it anyway.
Right, exactly, yep. Okay, so let's talk a little bit more about the syntax here. So as I mentioned, Verilog is case sensitive because people didn't like how VHDL was case insensitive. So you guys are used to that, obviously. You can't have names that start with numbers. White space is ignored, and comments uses a C-style comments. Right? Okay, so now the other thing that's confusing is I talked about this notion of flattening a design. So when you have modules, you have a language with modules, you're creating a hierarchy of design, and you're creating abstraction. You're abstracting details in modules that are used within other modules. However, when you synthesize it, everything gets flattened. But even when you simulate it, there's a consequence of this. There's a nasty side effect of having these modules. The side effect is that the same signal, the same physical wire, has different names depending on what module you're looking at it in, what the context, what the scope is. Okay, so here's an example. So now I've got this, well, first of all, I have two modules. The first question is, where do I start? One of these is the top level module, and one of these is a leaf module. And there's really no easy way to figure that out other than just reading it. You can see that this My Design has, it instances the AND3 module, right? Which means that My Design is the top level module, and the AND design is the bottom module, right? So this is kind of the root of the design. Now, the problem is, you know, if you go to GitHub and you look at a SystemVerilog code folder, you know, you're going to see 100 Verilog files in there. There is no indication of what the top level, I mean, unless they might name something top.sv. But looking at a list of Verilog files, you have no idea how they're organized hierarchically. Unless you like read them, right? Right. So I'm just giving you two files here. This is the top, and then inside My Design, I've got this signal called N1. And what I'm doing with that is I'm connecting it to the Y port. So on the AND3. So the AND3 has inputs called ABC and an output called Y. You might think that those are arguments, but they're not arguments. They're ports. But they look like arguments. They look like function arguments, but they're ports. Yes? Well, they're representing ports, like the top-level interface, like the I/O spec. So what's happening is that I'm instancing the AND3 module. I call it AND gate, but again, that name is irrelevant. It's just there for, you know, like when you simulate it, you can see those names. But you don't use the name for anything other than the simulator, right? And then I have this, when you instance the AND gate, you use a kind of a Pythonic style syntax here where you say .y. The .y refers to the Y port on the AND gate. So that's, you know, what they would normally in a programming language call the formal parameter, right? The formal argument Y, and N1 is the actual argument, N1, right? But in the case of a port map, Y is the port on the AND3 module, and N1 is the name of the signal. I'm connecting it to it within the context of My Design, right? So you'll notice that N1 is declared as a local signal, internal signal, N1, declared as a logic. I'm connecting it to the .y, but the problem is now is that that same signal, that same physical wire, now has two names. It's called N1 inside this module, and it's called Y inside that module. It just depends on what module you're looking at, right? But when you synthesize it to the hardware, it gets flattened in a way where that is literally just one wire, just with two different names. So this creates a problem when you go to debug designs on hardware, because when this gets synthesized into the physical design that goes on the FPGA, into the database file, which is called a bit stream, it only retains one of those names, but you don't know which one it retains. So when you go looking for signals inside of a synthesized design, you don't know what to look for. You don't know if it's going to be called Y or N1. It could be either one, because they get merged into one signal. Does that make sense? So yes?
Because of the logical behavior is same, that's why we are using same circuit but different names for different modules.
Well, it's just a way. So the modules just make it easier to read, and it allows you to basically write. It allows each individual module to be shorter in terms of the code, right? Like as opposed to, like if you flattened it in the SystemVerilog, then the modules would be very big. You want the modules to be small, so you end up having a lot of this hierarchy. But what ends up happening is that you know, the same signal might have different names. Now they don't have to. I could have called this Y in here, in which case it would have been called Y here and Y in there. But that's usually not the case. Usually they'll have different names, right?
The logical behavior is same.
Yeah, the behavior is the same. It's just, now the other thing though that's kind of bad about this is that, remember before I was talking about signals in conflict? So the problem here is that Y is an output, and B, A, and C are inputs. Notice I deliberately scrambled the order too of the ports. So up there it's A, B, C, Y. Down here I'm using Y, B, A, C. So I just scrambled them just to show that that's possible. But Y is an output and B, A, and C are inputs. But how would I know that from reading that? You don't. There's no indication whatsoever. But that's bad, because if that's an output, that means that I have to be careful not to have any other circuit try to set the value of N1, because that'll cause a conflict, right? But there's no indication in Verilog which one of these outputs, which one of these signals is an output, right? The only way to know is, well, you have to kind of know what AN3 is doing. You have to kind of understand the purpose of AN3, right? So sometimes people will put comments. You can put comments in there and say, hey, be careful, why, and don't, and N1 has to have a single driver, right? Yes?
Verilog assigns the name to a wire or
You mean the names here? Oh no, you do that. You name them as the designer, right? The names are mangled though when they get synthesized, when they get like converted to the design that actually goes on the FPGA. That's stored in like a database. Sometimes you get a little insight into that if you go into they have this thing called Signal Tap. They have like these debugging tools. Sometimes you'll get the peek at what they're called, like in what the cool tools call them, and they'll mangle the names. They'll add a bunch of machine-generated stuff to them. But in terms of in the SystemVerilog level, you choose the name.
So that's the case where I can have it assign both of those to that wire.
You could, yeah, you could do that, yeah. But that's not, generally like you'll have in your top design, you'll have a bunch of wires. Like for example, in the CPU, you're going to have an ALU, and the ALU has two inputs, A and B. Generally, ALUs have A and B are the inputs and C is the output. That's how your ALU is set up. But the A and B inputs are not called A and B in your CPU. They're called register number 1 and register number 2, or read data 1 and read data 2. So in your CPU, you'll have a read data 1 in the CPU, but then if you go inside your ALU is going to see it as A internally, right? But when it goes on the FPGA, it's the same set of wires. Yes?
Just to double check, you're saying that you can provide the arguments in a different order?
Yes. Yeah, just like in, you can put them in whatever order. Now, you might say, why complicate it? Well, the reason that they use this syntax is because modules often have like tons of inputs and outputs, right? This is a little misleading. It's very uncommon to see any module with 4 inputs for ports. Usually they have like a couple dozen ports. And so typically, you'll see them, like I said, arranged on multiple lines, There's usually a lot. It's not like a function in a regular programming language that usually only has a handful of parameters. They're usually a lot. Yeah. Okay, so here's a little bit more of an example. So in this case, I've got a module called NAND3. This is purely structural code. Why is it structural? Because all it does is instance other modules and connect them, right? That's structure. Then I've got inverter and AND3. Those are purely behavioral modules, right? Now you can mix and match structural and behavioral code in the same module if you want. In this case, I didn't do that though. So I've got the NAND3, which on its surface, you can see if we work from top down, it's got A, B, C inputs, Y output. It's called NAND3. And the first thing I do is I instance this N1, which is an internal signal. And then I instance AND gate. So the name is AND gate, but the module that it's instancing is called AND3, just like in Java or C++. And then I've got this thing called inverter, and it's type INV. And so those go in, and then you connect everything. So basically, the AND gate, this part right there, it says dot A is A, dot B is B, dot C is C, and dot Y is N1. That's what establishes these connections. So I establish the port map is what hooks everything in. And then again, these names are, if you use the same wire name in 2 different places, they're shorted, right? It follows the same rules that SPICE does, like you might have used in electrical 221, 222. So this N1, notice, is referenced here and is referenced here. And the reason is because I'm plugging these two modules in. I'm plugging the output of this into the input of this. And that plug is established just through the name N1, right? So N1 is the name. And then the inverter is I put N1, I connect it to A, and then I connect Y on the inverter to the Y on the global output for the NAND, right? So basically, instancing these creates the structure, and the port maps are what that actually hooks all the signals in, right? Okay, so then once you have that set up, then you could simulate this, and you would typically show it on a waveform editor like this. So you can see that A, B, and C are being toggled. Now this is a little misleading because, again, A, B, and C are being driven by an unknown force here. In reality, I use tickle commands. So the simulator has a scripting interface called tickle. Tickle is TCL, stands for Tool Command Language. A lot of CAD tools use tickle for interacting with it. I used tickle commands to force A, B, and C into this counting sequence where I fully, sort of enumerate all the input combinations of A, B, and C. Obviously, that's only practical because there's only 3 of them. Or, you don't normally simulate using full enumeration of inputs because there's too many. And then you can see why there's a corresponding Y value shown here. So you'll see that it's an AND gate. So as expected, the only time Y is a 0 is when A, B, and C are 1, right? And you can see that I go through the whole counting sequence 2 times there, right? Yes?
So is the internal signal absolutely necessary or just for count?
Yeah, in this case it was. The only way to connect that AND gate to the inverter is through that N1 internal signal. I don't.
So you can just say that this connected to the internal signal there that connects to both.
Yeah, that's the only way to do it I know of. Maybe there's another way that I'm not aware of, but yeah, that's the only way to get those guys to talk to one another. Okay, all right. So let's go through. Let me see if I can. I wonder if I can quickly do a demo of this. All right, so let me show you just in practice how you do that. So if I create. Let's create the and3.sv. Okay, so normally these would be in, each module is in its own file by convention. So and3, input logic A, B, output logic, what was it? Y, oh, there's a C too. Okay, so input logic ABC, output logic Y. And then inside, I'm going to assign Y to be A and B and C. And that's it, right? Yeah. So that's it for that. And then we're going to, what's that? Hold on. Did I screw something up? Oh, yeah, sorry. Thank you. Comma, forgot the comma. There you go. Okay. And then I had inverter.sv, and that was module inverter, input logic A, output logic Y, and that was input logic A, output logic Y. Cool. Okay. And module, and then assign Y equals tilde A, right? Not A. All right, and then I had and NAND3. Yep, and that's an NSV. And then, so that's module NAND3. Now in this case, I'm going to do something a little different. I'm going to have this have input A, B, and C, and output, and this will be input logic, and then output logic Y, and module, and then I'll still have the logic N1 because I need that internal signal. And then I can say, now this is generally what I do. If you open and3, sorry, test, what do I call it, temp? It's temp. test, no, and. Yeah, so if you take this and you just copy this, this is my super lazy way of doing that. So I just copied that, and then I'll say, my and 3, whatever. And then you can just kind of modify this. So I can say dot A gets A, dot B gets B, dot C gets C, and then let's delete that and say dot Y gets N1, connect that to N1. And then inverter, my invert, whatever, doesn't matter, it's useless anyway. Dot A gets N1, and dot Y gets Y. Whoops, Y, right? So that should connect everything. All right, so once I have that set up, now the better way to test this thing is through a test bench. So I'm going to create this test bench. I'll talk more about test benches a little later, but this will be a module called test bench. Yes? Oh, okay, I'll get it. That was in NAN 3. Oh, you're right. Yeah, thank you. Should be a comma. Okay. All right. So up here in the test bench, notice I don't have any inputs and outputs on the test bench. And so I will create logic A, B, C, and Y. And then I'm going to create this. I'm going to put this thing called initial. And this initial is I'm going to use this to initialize A. And I know the syntax is a little different than I'm not putting a sign here. So I'll talk about this more in a minute, but the assign statement is used when it's outside of one of these initial or always blocks. And I'll get into more details in that in a minute. So we've got A is going to be 0. Actually, I'm going to do this. I'm going to take a shortcut. I'm going to say ABC is going to get 3 bits of 0. And then I'm going to say always begin and then end. And then I'm going to say ABC is going to get ABC plus 1. And then I'm going to impose a 5 simulation unit delay. All right, let's see if this works. I don't know if this is going to work. Okay, so I'm going to type vlog. This is how you compile the software, the Verilog. So vlog is the compilation command. So I'm going to say vlog star. I don't know if you saw that, sorry. Vlog star.sv. What that does is, if you look in the directory after you do that, it creates a subdirectory here called work. Work is the library that you've compiled those modules into. So then, when you want to simulate it, you type vsim. And actually, I should have typed vsim-tb, but that's okay. So I launched it. I'm not simulating anything. But you notice there's a work here. I don't know if you can see, it's kind of small. There's this work library along with this other stuff. And you can see the TB. So if I right-click and I say simulate with coverage, it opens up the simulator. And then I've got the TB there. But here's the problem. I got to say start simulation and go into optimization and say full visibility. And then click on TB again because it optimized all my signals out. Okay, so now you can see I've got the TB and I've got A, B, C, and Y in there, right? Now, I forgot to actually instance my design under test, didn't I? Yeah. So inside of here, I need to also add what I call it, NAN, was it NAN 3? Yeah, NAN 3. And then I'm going to connect A to A, B to B, and C to C, dot C to C, and dot Y to Y. All right, so I'm going to save that. I'm going to recompile it. So vlog star.sv. All right, then go back here. I got to restart the simulation. So once I do that, you can see now, look at that. Foo has a little, I can drill down into Foo, and I've got my my thing there. So I can right click this and say add to wave, and I can see it in my wave here, and then I can simulate it, and whoop, didn't work. You can see I've got X's there, right? So what is going on there? btb.sv ABC. Let's try this. Let's say logic 2 down to 0 test sig, and I will set I will assign A, B, C to test sig, test underscore sig, and then I will set this to 0, test sig, under initial test sig, and then this will be test sig is test sig plus 1. See if that works. All right, vlog star.sv. You can see that we have X's here. So that's a bad thing. Remember, X is one of the 4 states of logic you have in Verilog. Okay. Also, you'll notice that A, B, and C and Y are all 1 bit. But this test signal is 3 bits, and I'm sure you can't see it in the back, but it says 3 there. Okay. So the problem here is, as it turns out, if you look at the test bench, there's a bug in here, and the bug is, and I'm also going to talk about this in more detail, but I just wanted to give you a demo. The issue is, you'll notice that I'm using when you have an assign statement, assign statements are statements you can put just anywhere in your Verilog module. They're meant to be kind of mixed in with the structural code. And so I assign the test signal, and you'll notice there's a single equal sign here, right, for the assign. And all the assign statements have an equal sign. But these other 2 assignments that I do in the initial block and this always block, notice it has less than equal, okay? So there are 2 different ways to assign signals called blocking and non-blocking assignment. As it turns out, I forgot about this, in the initial block you want to use a single equal sign. And I'll talk more about this a little bit later. So if I change that, I can recompile. So vlog star.sv, and then just restart the simulation. It should load in the updated binary. And there, now it's working. So you can see that. I can also zoom in here, and you can see, yeah, so you can see the waveform, and by the way, you can also see, oh, wait a minute, I kind of brushed past this, but when I ran it, there's a button up here that advances the simulation. So it runs it. So every time you hit that, it runs it for 100 nanoseconds. The nanoseconds is meaningless because there's no delay being modeled here. So, you know, it could have been 100 picoseconds or 100 femtoseconds. It doesn't matter. They're just simulation. The simulation unit, I think, in here is a nanosecond in this case. Okay. You can also see down in the lower left-hand corner, well, you can't see in the back, but it says now 200 nanoseconds. So that's currently how far you've simulated for. But the cursor is at, right now I've got the cursor at 119 nanoseconds, okay? You guys with me? Okay, now, so basically the test bench is actually setting the input signals. So A, B, and C are being set by the test bench. Y is being set by the design under test, which is the NAND gate that I designed, right? And then this test sig is like an auxiliary signal that's used by the test bench. There is another way you can do this. If you go to simulate, and then we go to start simulation again and go to work, let's say I select the NAND gate now, right? So I hit OK on that, and it should restart. Okay, so now the top level design, you see this, the top level design is the NAND gate now. So I've set this as the root of the design. And so I have to redrag these signals in again. Okay, so now when I run it, you'll notice that, check this out. These are blue lines now. So blue is the Z. Remember I said there's X and Z and 0 and 1. So Z is the undriven state, the tri-state. So A, B, and C are Z, and Y is an X, because it doesn't know, Y is being driven by logic, but it doesn't know what to drive it to because the inputs are Z, those high impedance inputs, okay? So now what do I do if I want to test this then? Well, if I don't have a test bench, there is a shortcut here. You can type force A1, force B1, force C, let's say 0, right? And then you can hit run. And what happened here was that I used these commands to set the inputs. These commands are actually in a language called Tickle, but it doesn't look like a language. It looks like they're just commands, but technically these are Tickle operations, commands. And then you can see that I was able to force the inputs and then get a corresponding output. You can also do it through the GUI. You can right-click on A and you can say force in here and set it in here. There's different ways that you can go about this, right? You guys with me? Okay. All right, so that's Model Sim. I want to go back to talk some more about Verilog then to fill in some of the gaps here. So we talked about structural modeling. This is where you take modules and you instance them kind of like objects in a object-oriented language, and then you connect their ports, right? Generally, these modules are all in their own file, where the file name is named after the module with the .sv extension. That's the convention. I think you can put more than one module in a file, but that's generally not done. And then you can simulate this in Model Sim, as I showed you there. You can also have, I already showed this, but you can declare a logic signal as having multiple bits, but the syntax for this is wild. This is unlike any other language. So, you know, like every language has a notion of an array. Well, except Python, I guess. But most languages have arrays, this thing called arrays, right? An array is when you have a variable that has, multiple elements. And generally arrays are associated with the bracket symbol, right? But like when you declare an array in C, you'll say like int a bracket 10, it creates an array of size 10. The brackets come after A, right? But in Verilog, they come before. So if you want to create a multi-bit signal, which is like an array of bits, you would put the brackets before the name of the variable when you declare it, right? So you would say logic, and then instead of just giving the size, you give it, and to be honest, I don't understand why they do this. You have to give it a range. So instead of saying that A and B are a 4-bit signal, you say logic 3:0. That's meant to represent bit 3 down to bit 0. And inclusively, 3 down to 0 is 4, right? So if you want to declare a signal with n bits, you have to say n-1:0, right? I don't know why they force you to do the :0 here, because as it turns out, you could also put 0:3 and it makes no difference at all. It's not like it reverses the bits or anything like that, right? Or at least when you declare it, right? So that's how you declare a multi-bit signal. And notice here that in this case, I'm declaring this as an input in the module, but of course you could also use this logic 3:0 to declare an internal signal as well. But because I said logic 3:0 A comma B, B is going to inherit, the type from A. So A and B are both 4-bit signals, and then likewise I have 4-bit outputs here, 1, 2, 3, 4, 5 of them, right? You guys with me? So that's just a multi-bit signal, and then when you simulate it in Model Sim or Questasim, it'll show you like all 4 bits if you put it in binary, but you can also tell it to represent these as decimal numbers or hexadecimal or octal, or I think they even have a way that it'll interpret these as floating point format too. So you just right-click on the wave editor. The wave editor, you just right-click and say radix, and you can pick which base it uses to represent these. You guys with me? So yeah, so in this case, this is basically just doing bitwise operations in this module. So the module has 2 inputs and 5 outputs, and each of the 5 outputs is a different bitwise operation of the 2 inputs, and then when you simulate it, you can see that here, okay? All right, so that's the multi-bit signals. Now this is the other thing that's really important, and you'll probably want to use this in your lab too. So Verilog has a ternary operation, which is a question mark. It turns out they have this in C and C++ and Java, but hardly anyone ever uses it in those languages. In Verilog, this ternary is used a lot because basically what it does is it gives you a way to create a multiplexer. So what you do is you say, if you have an expression and you have a condition, right, followed by a question mark, then that expression will evaluate to whatever comes after the question mark if the expression was, or if the condition is true. And it'll evaluate to whatever comes after the colon if it's false. So in this case, if I say assign y equals s question mark d1 colon d0, that's creating a multiplexer where the s is acting like the select, right? And then y is the output, right? So if the select is 0, it's going to output d1. If the select is, if the select is 1, it's going to select d1. If the select s is 0, it's going to select d0, right? You can also nest these, right, to create kind of like an if then else. So in lab 2, your goal is to create a 7-segment decoder, and you could do it with just one assign statement with this nested trinary, right? There's other ways to do it too, but that to me is the easiest way to do it, okay? Just make sure that if you have a nested version of this, you have kind of a catch-all, else on the end, and I'll show you an example of that too in a minute. So this is in this case, I have a 2-to-1 mux where the inputs and outputs are 4 bits, okay? Now, by the way, it's very unlikely that you'll ever build a mux in its own module, right? You can do that, and that's what we did here, but actually it's more common to take this line of code, this little single line of code that creates a mux, it creates a mux behavior, and you can put it in line in like structural code, to create a mux, right? That's typically how it's done, right? So this is a way that you can quickly deploy muxes, or if you want to create a module for it, you can, but it seems like a lot of effort to just, wrap that one line of code up, okay? All right, so then I already showed you this too. You can declare internal signals. In this case, this is a full adder. So this full adder has 3 inputs, A, B, and carry in. It calculates the sum and the carry out. And in order to calculate the sum and the carry out, it has these intermediate signals called P and G, which stand for propagate and generate. And so the P and G are declared internally, they're assigned internally, and then of course, then I've got 2 more assignment statements to assign the outputs, right? Now remember, this is concurrent semantics, so the order of these lines of code do not matter. You could scramble these in any order you want. It doesn't matter because anytime any of the signals on the right-hand side of the assign statement change, it'll activate an event that'll trigger that assign statement, which then can subsequently trigger other assign statements, but it doesn't matter what order they're in. So if A or B changes, it could potentially cause a change in P, which then subsequently will cause a change in S, for instance, right? And so this creates a chain of events that will happen. And I mentioned last lecture that if you have a cycle of these, it could lead to an infinite loop because it'll just infinitely trigger events, right? In this case, there's no loop because there's no feedback here. It's just A, B, and C enter the inputs, and S and C out are the outputs. Okay. Okay. So operators. This is pretty standard. This table has the common operators in Verilog and their precedence. This is the order of operations. Now, this is a little weird. There's a few things that are strange here. One of the things you'll notice is that there's an arithmetic shift. You guys remember the arithmetic shift is when you shift and if you shift right, you shift in the sign bit. Now, the first question you might ask is, okay, fine, but why is there a left arithmetic shift? That makes no sense. Yeah, it doesn't. I think they have that there because if the shift amount is negative, it'll make it a right shift, right? I think that's why. Now, you might say, well, wait a minute, why doesn't Java and C have the same kind of arithmetic shift operator? They don't because in those languages, the choice between an arithmetic or a logical shift is defined by the type of the value being shifted, whether it's declared as being signed or unsigned. So if you shift an unsigned int, it'll be a logical shift. If you shift a signed int, it'll be a arithmetic shift. But in Verilog, you don't have you often just have logical values that are not they don't have a sign, they're not signed, right, in the data type. But there's exceptions to that too, which I'll get to in a minute. But so they have this arithmetic shift. You'll also notice that there is a, oh, it's not in here. Yeah, it's not in here, but I thought it was in here. But the equal and not equal. Equal is equal equal. Not equal is bang equal. You guys know about that. Except in Verilog, there's another version of this that's equals 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 and bang equals equals. The reason for that is because of the four-state logic. If you're making hardware that you intend to synthesize, right? If you're making hardware that's supposed to be real hardware can only compare 0 and 1, right? It can only compare defined values. But remember that when you simulate this stuff, you can also have z's and x's, right? So if you have an equals equals and either side of that equals equals is a x or a z, then the entire expression is then going to be x, right? Because if you have a comparator in hardware and you give it an undefined value, you're going to get an undefined output. However, if you're writing a test bench, which is not meant to be synthesized, it's meant to just be run as software essentially, right? That's like the test bench I showed you. Then you can use the equals equals equals, which will actually is capable of comparing like two undefined values. And if they're both undefined, it'll evaluate to true, right? In other words, x equals x, right? Whereas in hardware, x doesn't equal x. X equals x is unknown because everything's unknown, right? You guys with me? So you might see that. And then of course there's the ternary. Oh, and then you also have these weird ones like, check this out. There's a NAND operator, tilde ampersand. That's not in Java or C, right? Can't do that. That's unique to Verilog, right? So that actually creates a NAND operation. Likewise, they have an XNOR, which is tilde caret, and tilde bar is XNOR, okay? Okay, so then one other thing, you guys have seen this already too, but whenever you have a numeric constant in Verilog, meaning a number that you type in, you have to define the number of bits that number should be interpreted as having. So if I type in, let's say 5, right, it doesn't know how many bits that 5 is supposed to comprise of, because if it's more than 3 bits, 5 only requires 3 bits, right? 1, 0, 1, right? But I might be assigning it to a signal with 10 bits, in which case I have to pad it with 7 zeros, right? So the way you're supposed to do this is anytime you have a numeric constant, you have the number of bits and then an apostrophe and then the base, which can be hex or decimal or binary or octal, and then the number. So for example, you might have 3 apostrophe B101. That means 3 bits, binary value 101, which is 5, right? We know that as 5, right? Or you might have a longer bit string like 8 apostrophe B and then 8 bits. But once you get 8 bits, it starts to be hard to read like a sequence of 8 bits. So they allow you to use underscores to separate groups of bits, but the underscore is ignored by the compiler. So the underscore is a way that you can put like bit fields in there in a constant without having to, and it makes it a little easier to read, right? So that's all that's going on there. For example, you can also put 6 apostrophe O42. O42 is octal 42 at base 8 and 6 bits, right? So in octal, every octal digit has 3 bits, right? And so obviously, you can fit 42 into 6 bits. Hexadecimal is H, that each digit there is 4 bits, right? Okay? All right, moving along. There's also this, very commonly you have to do bit manipulations in Verilog. So if you want to concatenate values into a single bit string, you just enclose them in curly braces and put commas. So for example, if I type a sine y equals A, and notice here I'm also doing bit slicing. So in this case, A is a multi-bit signal. I use brackets 2:1 that extracts 2 bits, being bits 2 and 1, which is the second least significant bit and the third least significant bit. So bits 2 down to 1. And then I'm going to put a comma and I'm going to concatenate it with whatever comes next. Now, this is another trick you can do. This is a duplication operator. So you can take bit 0 in the signal B, which is the least significant bit, the rightmost bit, and you can create 3 copies of it. Now, in order to do this, you have to have 2 enclosing curly braces. So you have to have curly brace, duplication factor, curly brace, what you're duplicating, curly brace, curly brace. If you don't have 2 nested levels of curly braces, this duplication won't work, okay? And then I combine this with bit 0 of A, followed by a 6-bit numeric constant, which is 100010. And if you do this, this will just create a 12-bit signal comprised of this, right? So yeah, you could also put that on the left-hand side of an assignment, which is pretty cool, right? So you can actually say assign A bits 2 down to 1, comma B 0, and put Y in there, right? So you could take Y and you could put it into these 2 bit fields, which I think is pretty neat. I only recently discovered that. Okay, and then like, for example, here's a way that you can do sign extension, which is, this is actually wrong for RISC-V. This is the way that MIPS does sign extension. In MIPS, remember there was a 16-bit immediate field in the I-type instruction. So you would have to take bit 15 and duplicate it 16 times to sign extend. In RISC-V, there's a 12-bit immediate field or a 20-bit immediate field, depending on if it's an I-type or a U-type instruction. So that's, you'll do, you know, obviously you just change the bit you're duplicating and the number of times you're duplicating it. But this is using the duplication operator to duplicate the sign bit to convert a smaller value into a larger number without changing a smaller number of bits to a larger number of bits without changing the sign. Okay? Alrighty, reduction operators. I don't think we'll ever use this in this class, but I think it's kind of cool. The reduction operator is a way that you can take a multi-bit signal like A, and you can feed all the bits of A into an AND gate and produce a single bit value. That's pretty neat, but no one ever uses that in this class. Okay, so let me get to Lab 2 specific stuff then. Okay, so I think you guys have enough information for everything in Lab 2, I think up until this test bench part. So here's basically, the idea is to create a hex decoder. The problem is that you want to be able to put the hex decoder in a module, right? I mean, you don't have to, but if you don't, then you have to kind of copy and paste the code. You have to, like, remember there's 8 of them, right? So remember we talked about the concept of regularity. Regularity is when you design one thing and then you can like kind of stamp it out a bunch of times. So the goal here is to create one hex decoder and then instance it 8 times inside of your design, right? So, but within that module, you can basically just put an assign statement, right? So you can use the ternary operator to basically do the 7-segment decoding, right? Now these numbers I just made up. I don't know if that's the right values, right? But that just shows you how the structure of that works, okay? And then, I already talked about model sim, skip that. Okay, right. So in Lab 2, I created this graphic because I felt like I wasn't explaining this adequately on Monday. So the idea is that you have 18 switches on these boards. And pretty soon we're not going to have that many because they discontinued this board and I can't find any other board with this many switches and hex digits and stuff. This board is unique. It's got so many components on it. They don't make boards like this anymore, right? But we have 18 physical switches and there's 8 7-segment displays. 7-segment displays are actually really 8-segment displays because they have a decimal point. But one of the problems with this board is they didn't wire the decimal point up, so there's no way to light that up. It's impossible. There's no PCB trace between the FPGA and the decimal point input on the hex displays, on the 7-segment displays. That's pretty bad. But we can control the 7 segments, which means that, you know, there's basically 8 times 7, 56 bits coming out of the FPGA directly in here, which is nice because you guys might have noticed, like, if you see a typical 7-segment display like this and you film it with a camera, it looks like it's flickering on the camera because what's happening normally is that they want to save pins. So generally, like when you have a 7-segment display, only one of them is actually driven at a time, and then they're kind of scanned really fast to trick, you know, it uses the persistence of vision of the human eye to make it look like they're all lit up when in reality only one is lit up at a time. But on this board, on this FPGA board, they actually have 56 bits going and driving all 8 of these hex displays. They're all being driven all the time. So if you film this with your camera on your phone, there's no flickering. These things are actually on all the time, which is kind of cool. And it also simplifies the logic because you don't have to worry about multiplexing the 7 bits. You can just drive them all. So in this lab, we want to connect the switches through a 7-segment decoders into each one of these hex displays. But as I mentioned on Monday, there's only 18 switches and there's 8 displays. So, and remember, when you go through the 7-segment decoder, we don't need 7 bits for these guys. We only need 4 because the decoder takes a 4-bit, base 16 hexadecimal value and converts it into a 7-bit value, which is then used to light up these segments, to create the number on here, right? So we're going from 4 bits to 7 bits on each one of these. But even then, in order to light up all 8 of them, we would need 4 times 8, which is 32, but we only have 18 switches, right? So basically, we just can light up, we can set the value of the lower 5, and actually the 5th one, we can only go to 3, right? 0 to 3. And now, the problem though is that I want you guys to create 7-segment decoders for these 3 that are always 0, because when we add your CPU to this, we'll gain the ability to write all 8 of them, right? So we still want to have decoders for these guys, even though the input to the decoders will just be hardwired to 0 for now. You guys with me? Okay, so basically if I switch 15 down to 12, that is going to allow me to put a value from 0 to F, right, on hex display 3, right, hex number 3, right? So that's the goal of the lab. So this is a purely combinational circuit. Now the FPGA has actually 18 physical wires that go from the switches into the FPGA, and they're just logic 0 if the switch is down, logic 1 if the switch is up, right? So this is active high logic. And the way this works is, we're going to give you the file for this, but the top level file that goes on the FPGA actually has to have inputs and outputs that match the special names of the inputs and outputs on the circuit board, right, on the FPGA, the way the pins are mapped on the FPGA. So you're going to have a signal called SW, which is an 18-bit signal that you're going to use that special magic name SW, which means when you synthesize your design, it will connect those pins to the switches, right? And so, yeah, so, these are the actual pin names too. Check it out, Y23. So this FPGA has 780 pins underneath of it, arranged as a 2-dimensional grid, a ball grid array, they call it FBA, field flip chip ball, FBGA, field flip chip ball grid array, FBGA, right? 780 pins. The rows are letters and the columns are numbers, just like in Microsoft Excel. So like this is Y24, row 24, row Y, column 24. These Microsoft type numbering here, okay? So, but you don't have to worry about that because these mappings between the names and the pins are already going to be provided for you in a project file that we're going to give you. Yes?
You can go back a slide.
Sure. Okay. Okay, now let's talk about the hex displays. As I mentioned, the hexes are 7 bits. The 7 bits are in a multi-bit logic signal, right? So it's like logic 6:0, right? However, there's 8 of them. So you would think you'd have a 2-dimensional array, right? There's 2 dimensions. There's like bits and then hex, right? But no, what they do instead is they enumerate each of the hex displays by name. So it's literally, they're called hex 0, hex 1, hex 2, and then each one of those is 7-bit array of bits, right? Instead of using a 2-dimensional array, which would seem to make more sense. Okay, now the hex displays are active low, meaning a 0 in any one of the segments turns it on and a 1 turns it off, right? Also, the bits are shown here, so bit 0, so the way this works is that if you read the hex value from bits on the right to the left, if you're going from right to left, bit 0 up, right, least significant to most significant, bit 0 is the top segment, and then it goes clockwise, goes 0, 1, 2, 3, 4, 5, and then 6 is the middle segment, right? So you have to go in that order and active load. This is all in the manual, by the way. The manual for the DE2 board is on Blackboard under downloads. I just grabbed this from the manual, okay? All right. Okay, so the way your design will work is there will be a module called top. Top is the top level module for the FPGA, for the hardware, for the deployment, for the physical system. So in that top, all the inputs and outputs of the top module have to match magic names to map to the pins on the FPGA. Every one of your inputs and outputs on the top level module has to map to a pin on the FPGA. If it doesn't, then the tools do something that I cannot believe they do this. This is the craziest thing. The Questasim will actually randomly assign pins to signals if they don't match the pin mapping, which means that if you don't have this pin mapping and you program the FPGA, you get like the board freaks out. Like there's all kinds of crazy, like the hex displays come up all random and stuff, right? So you have to make sure the top level module matches. But we're going to give you the top level module. It's called top, right? Now in that top level module, you'll notice that there's some clock inputs that we don't need in this lab because this is combinational logic. Clocks are only for sequential logic. We're not going to have that until the next lab when we have a clock signal for the CPU. So you could ignore that. There's 3 clocks. To this day, I don't know what clock 2 and clock 3 do. Never used them, don't know what they're for. I don't even know if they work. There's also a key input. The key input are the buttons. There's 4 buttons. You're not using those for this lab either. We'll use that for the reset in the next lab. And then the switch, obviously we'll use. The switch input is an 18-bit signal. It will have to be fanned out to your, well, not fanned out, actually. It should be split into different bit ranges to your hex drivers. They're called hex driver. I don't know. Charles came up with that name. He called them hex drivers. I don't care what you call them. They go to something that does the 4-bit to 7-bit decoding. And then you're going to connect the outputs of those to the hex outputs. As I mentioned, there's 56 total bits coming out, 8 digits, 7 bits each. Okay? And they're all enumerated through their name. Okay? So that's the top. However, we also want you guys to create a test bench, which means that you need another top module for the simulation mode, right? So SystemVerilog always has to have like a non-synthesizable test bench of some kind, as well as the synthesizable code that you want to put on the FPGA, right? So there's some things you can put in Verilog that make it non-synthesizable, like by putting delays in, like say wait for 5 units of time. You can't synthesize that, right? There's certain data types that can't be synthesized, right? So like if you want synthesizable code, you have to declare everything as a logic, right? So, but anyway, the top, so we're going to have this top level, SymTop. There's a module called SymTop. That's not going to have any inputs or outputs because it's going to consist of 2 parts. One's a tester that's going to drive the key, the switch. This is a virtual switch now. So you've got Verilog that's going to set the switch and pretend it's a human flipping the switches on the FPGA board. And then likewise, it's going to see the hex data coming in. So basically, what I'm doing here is I'm swapping the inputs and outputs. So on the design under test, I have inputs and outputs. On the tester, I'm swapping those so I can drive the inputs with an output on the tester and inspect the outputs on here with the inputs on the tester. You guys with me? Right? So this is called a SymTop, is the top level. You'll put the top inside there as well as a tester. So in other words, when you simulate, you're simulating this. When you synthesize, you're just synthesizing top, right? And this other stuff. So this, because you don't include the test code when you synthesize. Okay? All right, so we're going to give you a skeleton. So there's a file called lab_hex.tar.gz. That has some stuff in it that you'll need. It has a lot of stuff. It has some Verilog files that are going to be your template that you can start with. It also has a project file for Questasim. It's called, I think it's like labhex.qsf. I don't know what QSF stands for, but it's a tickle script that you run when you open the project, right? And that project file is what contains your pin mappings that map the magic names to the actual Excel spreadsheet pin things, right, for the FPGA. That's all in the project file, so that's all done for you. So all you guys have to do is untar the project skeleton, and then you put your designs inside POP and hex driver. I don't know, I think there's a hex driver. It's just empty though, right, because that's what you guys are going to fill in. And tester. You guys with me? Okay. Now we have a script. I know some of you guys have taken 313, right? Some of you. Yeah, 313. So 313 we use. You guys use Quartus. You can use Quartus in this class, but we wrote some scripts that still use Quartus, but they use it through the command line interface, the tickle interface. So we have a script called CSCE 611.sh. If you run that script, you can tell it to do test. You can send a parameter called test bench or build or program, and it'll actually run the test bench, compile, synthesize, right, or actually deploy the design on the FPGA. And actually, one thing I forgot to mention, the top design already has some code in there that you can use for testing. It's this little toy code that takes the LEDs on the board and makes the LEDs walk across the board left and right, right? That's already in there for you. So you can actually just unpack this project and say CSCE 611.sh build and CSCE 611.sh program, and it'll actually put a working design on the board that'll run. So it gives you kind of a starting point, right? When you build your design, you could put your design in addition to that stuff in top, right? Or if you want, you can delete that test code too. I don't care. Okay, you guys with me? Okay, so that's the skeleton. And, right, oh, sorry, here it is. Yeah, these are the commands, sorry. Test bench, program, and pack. Now, one of the problems with test bench is, I have a whole sequence of slides on test benches, but I mentioned that the test bench does everything. These commands are all command line driven, right? What that means is that if you run the test bench command on our script, it doesn't bring up the model sim GUI. It just runs the test bench, and the expectation is that your tester is going to test everything automatically, and if there's an error, it'll print an error message or something, right? The problem with that is that if you get an error, then how do you debug it? You don't have any, there's no way to do debugging in that case, right? So in other words, the test bench command will run the test bench, but if you end up with an error, you're going to have to open Model Sim and go through the steps that I just showed you, right? To actually see a waveform, if you want to see a waveform. You guys with me? Okay. We'll help you with this, by the way. That's why we have the lab and the TAs, so we can show you how to do this stuff. But just keep in mind, this is all text-based. Likewise, you can open Quartus. You can open the project file in Quartus and run everything through Quartus if you want the GUI for that too, right? You don't have to use these commands. Okay. Okay. So that's all I've got. Sorry, I didn't mean to take that long. I just want to get you guys up to speed. So I think I've covered enough of Verilog to perform the 7-segment decoder lab. The only thing I haven't covered yet is test bench design, and that is required in lab 2, but I'll cover that in lecture on Monday, and then you'll have all of next week to implement the test bench, okay? All right, thank you.